Okay, welcome back everyone. I am our CBT course, Theory and Simulation. The time has come to deal with perhaps the hardest topic in magnetic resonance, but at the same time one of the most important ones, the spin relaxation theory. Now the reason it's hard, you'll see in a few moments. It's quite a lot of very complicated mathematics, but the reason it's important is that relaxation theory analysis is used rather a lot in structural biology. In particular, protein structure determination, more general structural analysis, analysis of ligand binding and other such things rely quite heavily on a phenomenon called the nuclear Overhauser effect. And NOE is dipolar cross relaxation. It's a relaxation theory phenomenon with the amplitude that happens to be distance dependent, and so we can use it to extract those distances and then solve back for the protein structure. And we'll hopefully get to the nuclear Overhauser effect in due course, but today I will derive the most general case for rotationally modulated interactions. Now what I'll start with is something that's fairly standard, the time-dependent perturbation theory from quantum mechanics, and this is the starting point for a modification which we use in magnetic resonance called Bloch-Redfield-Langston's relaxation theory. It's one of the most successful spin relaxation theories out there, and well, we'll be deriving it today. So let's get started. Let's say we've got our usual Schrodinger's equation, d by dt psi is minus I h of t psi, and that's a differential equation because the Hamiltonian is usually a bunch of operators that involve derivatives. Let us transform it, however, and try expressing it as an integral equation. Let's just integrate both sides from 0 to a time t. So an integral from 0 to time t of d by dt psi would be minus I integral from 0 to t h of t psi of t. I'll just start putting t explicitly on psi to emphasize its time dependence, dt. Now the integral of the left-hand side here is trivial. It's just psi t minus psi 0. Yes, the integral of a derivative is the original function with those limits. So what we get after we move the psi 0 to the right-hand side is the form that's strictly equivalent to the original Schrodinger's equation. It simply no longer involves a derivative on the left-hand side. It became an integral equation. So psi of t is psi of 0 minus I integral from 0 to t h of t1. Let's call it t1, the integration variable, to avoid the confusion because there will be quite a lot of these t's. Then psi of t1 dt1. Okay, that's an equivalent formulation, but it didn't get us very far. Instead of having to compute a solution to a differential equation, we now need to compute the solution to an integral equation, which is not in general a simpler problem, and in many cases is in fact a harder problem. So why don't we integrate it another time? So let's take this, substitute it back here, and take another integral. So I'll keep our left-hand side, but I'll stick this expression for psi t into the right-hand side here, and you'll see in a moment why I'm doing it. So d by dt of psi now becomes equal to minus I h of t applied to that thing there. So we'll have psi 0 minus I integral 0 to t h of t1 psi of t1 dt1. Opening the brackets, we got minus I h of t psi 0 minus 1 I h of t. So this h of t, and we get minus I times minus I is just a minus, so the I vanishes, and then integral from 0 to t h of t1 psi of t1 dt1. Right, well, let us integrate this again. this becomes psi of t, and there's a psi 0 over at the end, so psi of t is psi 0 minus I integral 0 to t h of t1 dt1 psi 0. So psi 0 is time independent, so I took it out of the integral, minus an integral from 0 to t h of t1, then integral from 0 to t1 h of t2 psi of t2 dt2. And this again is strictly equivalent to the original Schrodinger's equation, except it's more complicated. But there are a few things here that we can start noticing. You see, whereas previously, both here and here, we had our psi depending on time, so it was psi at some future point, which is yet to be computed. Increasingly here, on the right-hand side, we've got the initial condition. So the psi 0 here, and the psi 0 here, and we only have the time-dependent psi, for which we would need to solve itself consistently, in the very last term. However, what would happen if we continue this procedure? So we just take this psi, we stick it back into the Schrodinger's equation, we integrate yet another time, another term would jump in front of this, and it would have psi 0, and the residual term would have psi of t. Now, assuming that the norm of this Hamiltonian has been carefully scaled, or the times are small enough, this series, the terms of it might get smaller and smaller and smaller, and so at some point we might get away with truncating them. So what I've done in the handout is I've given you the result of applying this operation infinitely many times, so that we get a series, and the result is in fact known as the Dyson series, and what we get out of it is the following. Psi of t would be square bracket, unit operator, so that's just the initial condition that's multiplied by nothing, then plus minus I integral from 0 to t dt1 h of t1. You see, I've switched the integrals into operator notation, so this integration operator in front of it means integrate this with respect to t1. Then the next term in this, plus minus I squared, integral from 0 to t dt1, integral from 0 to t1 dt2, applied to h of t1 times h of t2, and so on. So there will be triple integral, quadruple integral, and so on. And all of that, nicely, is actually applied to psi 0, the initial condition. Now, those of you who have done the Southampton's Big Spin Dynamics course would recognize the series for a time-ordered exponential here. But what's important about it is, in certain situations, and we will be looking at exactly when that is true when we get to Redfield theory proper, this series converges. And when it converges, it can be made to converge reasonably accurately at the second term. The strict requirement for that is that the time steps should be small. They should be much smaller than the reciprocal norm of the Hamiltonian, and then the thing works. And the act of truncating this at some term is in the essence of the time-dependent perturbation theory. We include the first perturbation, the second perturbation, the third perturbation, and hopefully that's accurate enough, assuming that our residual here is sufficiently small. So finally, what we get in a slightly more compact notation is a sum from n equals 0 to infinity un operator of t applied to psi 0, where un are these integrals. So u0 is just 1, u1 is this integral, u2 is this integral, u3, and so on. So Assuming that we have chosen our time step to be sufficiently small, this can be truncated at the second term, so there is nothing more in here, just the psi 0, and that's the second order time-dependent perturbation theory. Now, this needn't be 0 in the lower limit of this integral, it could be some time t, in which case we would need to take a small step forward. So the final expression that we will find useful, at least in a philosophical sense, when we derive the spin relaxation theory is the following. So the second order approximation to psi at time point t plus delta t, so we take a small time step forward, delta t is assumed to be small, is equal to psi of t, the original function that we are correcting, hence the term perturbation theory, the rest will be perturbation to it, minus I, an integral from time t to time t plus delta t, h of t1, the integration variable, psi of t1, dt1, minus the second correction in here, integral from t to t plus delta t, h of t1, then another integral from t to t plus t1, h of t2, then psi of t, d, t1, d, t2. Now this should be psi of t in here. Plus the terms of the order of the norm of the Hamiltonian times delta t cubed. Now, assuming that this is smaller than 1, the residual would be small because the cube of a small number is an even smaller number. So essentially t has to be much smaller than the reciprocal norm of the Hamiltonian, or equivalently in physical terms, much smaller than the characteristic time of the system dynamics. Then this correction would converge and would be an appropriate representation for the perturbative function. This is used in optical spectroscopy a lot, where system response is required to some oscillatory field that we apply, which is put into here. But we will be using a conceptually similar theory, except it will be for the density matrix, for the derivation of our spin relaxation theory. Okay, that was the introduction. Let us now return to specifically the spin dynamics context. We have our Liouville von Neumann equation, so d rho by dt is minus I h of t commutator rho of t, where all three here are operators, or equivalently it's minus I h of t double hat rho of t, where h double hat is the commutation superoperator corresponding to the Hamiltonian. In a typical liquid, we have two conceptually different contributions to the Hamiltonian. There is one that is static or moves predictably, that is the Zeeman interaction, so the chemical shielding, J-couplings, which are orientation and magnetic field independent, and maybe radio frequency fields that we have applied, but those vary in a way that's either static or well controlled. But there's another type of contributions in there which in liquids arises due to the stochastic rotational motion of the molecules. We've got Brownian motion, they move around, they tumble, and they tumble in an erratic way on a nanosecond to femtosecond time scale. So in effect what we have here is minus I h0 plus h1 of t and rho of t, where h0 is containing all the static parts of our Hamiltonian, and h1 contains these stochastic time-dependent terms that come out of molecular motion. You remember from the previous lectures that interactions are anisotropic, so CSA, dipolar coupling, hyperfine coupling, things like that, they all have directional dependence, and so the rotation of the molecule would modulate whatever interactions that there are that happen to be anisotropic in the molecule. It is extremely difficult to treat such situations in a differential equation formalism. The noise is not mathematically well behaved, it is not differentiable, it is irreproducible, that is, from instance to instance we would have a different realization of the noise. And so the typical way of handling such situations is to try and build the formalism that would express this noise, not in terms of its explicit and fairly erratic time dependence, but in terms of its statistical properties. So various averages, dispersions, correlation functions, and things like that. Now, statistical properties of the noise are predictable. They are the result of averaging an infinite period of time, and if you look at histograms, for example, they're continuous functions, whereas the noise itself might not be. And so, our hope of treating such a system can only come to fruition if we find such a formalism. And of course, integrating this and trying to do something similar to the time-dependent perturbation series that I've just introduced would look like a natural way of transforming just the noise into the integral of the noise, which might be a bit smoother and a bit better behaved. And that is the general idea behind what it is that we're about to do here. Okay, so we'll make one assumption. It's the first assumption in quite a long list for this theory about H1. We will assume for now two things about it. That first of all, this noise is stationary, and mathematically speaking, it means that the statistical properties of the noise do not depend on time. The noise itself, of course, does, but let's say the standard deviation of the noise doesn't, and that's called the stationary noise. And the other thing we will assume about it is that its ensemble average vanishes. That is, if we take an average of that noise either over all the molecules in the ensemble or equivalently over a sufficiently long period of time, that it is zero. If the average is not zero, we just subtract it out and we put it into H0 as a stationary part. And so this is not in practice an assumption, we're just partitioning our Hamiltonian in such a way that that should happen. Okay, and the second assumption that we will make is the same as we had to make in perturbation theory, that the norm of this time-dependent part is much smaller than the norm of H0, and that is required for the perturbation theory assumption, for that series in integrals of the Hamiltonian to eventually converge. This essentially means that the truncation is permissible. Okay, so let us go ahead and try treating this problem in the same sense as we treated the time-dependent perturbation theory. The first step that I'll make, however, is slightly different. I will first move into the rotating frame, or a more strict word for it is the interaction representation with respect to H0, which in the case of just a usual NMR experiment would just be the rotating frame that we're all used to. The transformation might look a bit arcane, but I will demonstrate by just direct inspection that it accomplishes what is necessary. So what I'll do is I'll introduce a density matrix sigma, which will be related to our original density matrix by the following relation. It will be multiplied by the exponential of H0. So that and the new Hamiltonian H1R double hat would be E I H0 T, then H1 of T, E minus I H0 T. So let us substitute this new notation into the equation and, well, just see what happens. So our rho of T is related to sigma by the inverse of this transformation, and so what we've got is minus I H0 T, sigma of T, and our Hamiltonian, the original Hamiltonian, is related to H1R again by the reverse of this transformation. So h1 of t is e minus I h naught t, h1 r of t e plus I h naught t. So I'll just plug these into the Liouville-van Neumann equation and let's see what happens. So the derivative of this is just the product rule. So what we've got is d by dt of e minus I h naught t. I'll temporarily drop the double hats on this. It's just a bit tedious to write them. Sigma of t plus e minus I h naught t, then d by dt sigma of t. That is the left-hand side, so this, and then plugging that thing here and rho into there will get us the following: minus I h naught, then rho becomes this, e minus I h naught t sigma of t, and the h1 part minus I h1 becomes this, e minus I h naught t h1 r of t e plus I h naught t, and then the rho, which would be e minus I h naught t sigma t. You can start to see why I warned you at the beginning that this is going to be a lot of mathematics. It is unfortunately unavoidable. It's not possible to hand wave one's way through spin relaxation theory. This is the real thing. I'm not complicating it on purpose. Okay, let's just cancel a few terms here and there and take a few derivatives. So the derivative of this with respect to time is minus I h naught e minus I h naught t sigma t. Then this just remains unchanged. I h naught t, d by dt sigma t is equal to, a few things should disappear. In particular, this is equal to this, so we'll just copy it down, I h naught t sigma t, and then both of them just cancel on the right and the left. Then these two terms cancel here, the plus and the minus of the exponential. So we are left with minus I e minus I h naught t h1 r t sigma t. And then finally this thing here cancels with this thing here. So this also goes, and we are left with something quite simple. We get d by dt sigma of t, and I'll start writing the hats again, is minus I h1 r of t sigma t. Something disappeared. Can anyone tell me what that is? Yep, the h naught's gone. So you see, we did the transformation and we only now have h1 explicitly in the equation, and h naught has gone into the definition of sigma of t. Now the reason we did this is to facilitate the perturbation theory treatment. You see, typically the amplitude of this h naught is in the gigahertz. It's of the order of gigahertz if you're doing NMR, and of the order of terahertz if you're doing EPR, or well, even greater into the far infrared if you're using a really expensive EPR spectrometer. The order of magnitude of this, however, is kilohertz in the case of NMR and megahertz in the case of EPR. That is 3 to 6 orders of magnitude slower. H naught, however large it is, still generates a unitary propagator group. Yeah, you remember in our treatment of unitary groups, matrix exponentials cannot be large. All the eigenvalues the norms of them are equal to 1. And so this object, however fast the dynamics may be that it generates, has a small norm. And so what we've got here is a unitary transformation that hasn't changed the norms. However, what it did is it got rid of the very large interactions, replacing them by very fast motion inside this definition. But what it means in practice is we are left with a term with a much smaller norm. And that improves the convergence of the perturbation theory procedure. And we can now use it with much longer time scale than the original nanoseconds and picoseconds in there. Okay, so with this in place, and you can see it looks, although it's a density operator treatment, on the surface this is basically Schrodinger's equation. Here we can just stick the usual brackets into here, and in Liouville space this would be a state vector, this would be a matrix, and the treatment is isomorphous to the sort of treatment that you've got for the wave function. And so let's just take this equation and stick it straight into time-dependent perturbation theory and see what falls out. We'll have to make a few additional assumptions, quite a few, but we will get an expression in the end that will be containing not the actual instance of this noise, but its statistical properties, and that is much more convenient in practice. So here's our rotating frame version of the Liouville van Neumann equation. So d sigma of t by dt will be minus I h double hat rotating frame of t sigma of t. And let's integrate it in time just as we did in our perturbation theory treatment. So sigma of t minus sigma of 0 on the left hand side and minus I integral from 0 to t h1 r double hat of t1 sigma of t1 dt1. So we've transformed it into the integral equation. Let's take this initial condition to the right hand side and resubstitute it back into the original equation. So then d sigma of t by dt would be minus I h1 r of t sigma of 0, then minus integral from 0 to t of h1 r of t. Notice this is t not t1, I've pulled it inside the integral, h1 double hat r of t1, and sigma of t1 dt1. So this is just the result of substituting this equation back into the original differential equation. Let's now do the following. We will take this equation and we will apply the ensemble averaging to both sides of it. So I'll just put the angle brackets around on the left hand side and on the right hand side, which indicate ensemble average. We're averaging over every molecule in our sample. Now clearly an averaging is a linear procedure, so a derivative of an average is an average of a derivative therefore, and so what we've got here is d sigma of t by dt, then minus I, an average of h1 r of t. Now sigma naught, the initial condition, we assume to be the same for every molecule in the ensemble. So it's non-stochastic, it doesn't depend on which molecule we choose, and so for the purposes of ensemble averaging it's effectively a constant vector, and so it can be taken out of the ensemble average here. So this is the ensemble average of that, and sigma of 0 minus an integral from 0 to t, and then we've got a fairly complicated ensemble average here. So h1 r of t, h1 r T1 sigma of T1 dt1. Okay, we can say nothing about this for the moment, but what we can say a few things about is this. Let us take this operator and return it back to the lab frame. If you remember the definition of H1R, it was equal to E plus I H naught T applied to H1 of T E minus I H naught T. Ensemble average. But the H naught, by our assumption, is the part that does not depend on orientation and isn't time dependent in a way that would be different for different members of the ensemble. And so this, for the purposes of the ensemble average, does not change between the different molecules, and so it can be taken out of the ensemble average. And so we can take these brackets, therefore, and we can pull them in here. But the ensemble average of this at the very beginning of our treatment we had set to 0. And so the whole thing is in fact 0, and therefore this first term completely vanishes. So we are left with a slightly simpler equation, d sigma of t by dt is minus integral from 0 to t, ensemble average h1 r of t, h1 r of t1, sigma of t1, dt1. Right. The next thing we need to do here is to try and hack apart this time-dependent rotating frame Hamiltonian in a way that would be perhaps slightly more amenable to treatment. What I will do here is the following thing. I will observe that matrices like, for example, this, A of t, B of t, C of t, and D of t, so time-dependent matrices can be written out in terms of constant matrices with time-dependent coefficients. So this would be A of t times 1, 0, 0, 0 plus B of t times 0, 1, 0, 0, and so on. Clearly, it is always possible to write a time-dependent matrix in this way. And so what we will be doing is trying to expand this Hamiltonian in exactly such a way. And from the theory of rotations, you might remember that we had those rotational decompositions, and this is fundamentally why I am doing it, because we will then assume that the motion is rotational. These coefficients will become Wigner functions, these will become irreducible spherical tensors, and then the entire theory will actually collapse quite conveniently into reasonably computable expressions. And so what I'll do is introduce the following notation. I will say that h1 of t will be a sum over k, qk of t. These are those time-dependent functions, like those, applied to some static operators qk. Now, because the Hamiltonian is Hermitian, the same holds for the Hermitian conjugate, and so this happens to be equal to a sum over k of qk star complex conjugate times q double hat k Hermitian conjugate here. And of course, if we apply a rotating frame transformation to this, q is just a scalar, so it's taken out, and so these operators would get transformed into this rotating frame. So what I'll do now is I will plug this in place of this Hamiltonian, and I will plug this in place of this Hamiltonian. And the reason why I'm doing it that way, so I'm putting one in a direct form and one in a conjugated form, you may remember our definition of a scalar product many lectures ago when I was dealing with Hilbert spaces. There was a necessity to have one of the terms conjugated, and that's basically why it will be a bit more convenient later on. So let's plug this here with a t and that here with a t1 and then see what happens. And I'm starting to use the handout here because the mathematics is getting big. So d by dt of our ensemble averaged rotating frame density matrix sigma t will be minus, it is now a sum over k and m, because there's a sum here and a sum here, and I'm just using different indices. From 0 to t is integration, and then simply just plugging it in and writing it out. So it will be q k of t, then q m star of t, then q rotating frame double hat k of t, then q double hat rotating frame Hermitian conjugation dagger m of t1, and then we've got sigma of t1, the density matrix, closed ensemble conjugate bracket, ensemble average bracket, and close the integral. At this point, we need to introduce extra assumptions, otherwise this would not be treatable. What we need to do is the following, and this is where the perturbation theory comes in again, and our original assumption that the perturbation term is small is necessary to justify this particular step. Now this is one of the least physically clear steps in the whole theory. If you would like to have full justification for it, you'd have to look through the original literature. We don't really have the time to properly justify it. But I'll just give you the hand-waving explanation. You see, we have sigma of time, the system density matrix, and the time-dependent Hamiltonian under the same ensemble average bracket. Those of you who did statistics in your undergraduate course might remember that the average of a product separates into product of averages if and only if the functions are uncorrelated. And that's the assumption that we will make. I will assume that the noise in the system is so weak as to relax the system, so it affects the transitions and the system falls into equilibrium, but not drive it. So the system remains uncorrelated with the noise that's present in the Hamiltonian. In other words, the noise is sufficiently strong to relax the system, but insufficiently strong to take it with it and lock it. And so what we can do under that assumption is separate out the average for these two functions, these two are deterministic, and the average for the density matrix. And so what we are going to have, therefore, after we have made that assumption, is minus integral ensemble over km, integral from 0 to t, ensemble average for q, k, t, q, m star t1, ensemble average bracket. Then these two are rotating frame transformed stationary non-time dependent matrices, and so they are just the same for every member of the ensemble, so they are constant matrices. If we take, if you freeze the times and just look at individual different molecules, so they do not contribute to the average. So we've got the q, k, r of t. It's of course time dependent, but it's the same for each member of the ensemble. Qm double hat r dagger of t1, and then we've got the ensemble average for sigma of t1. T1. You see what happened? We had a joint ensemble average. We had assumed that the system is uncorrelated with the noise, and the joint ensemble average has split into a product of ensemble averages. And what I'll do also in the subsequent treatment is just for convenience, because they will always be there from this point onwards, I will remove these angle brackets from the density matrix. So from now on, we will simply assume that we are dealing with the ensemble averaged density matrix. So here's our equation as it stands at the moment, and there is something that is fairly peculiar in it. That is this bracket. If we look at what it is, qk of t, qm star of t1, it's a function at a time t, then another function at a different time t1, ensemble, averaged over instances. Objects of this kind in mathematics are known as correlation functions. And we'll just denote one, g, and it depends on the two indices k and m, what exactly gets correlated, and it depends on t and on t1. This is where the other assumption that we made at the beginning of the lecture comes in. You remember that I had assumed that the noise in our system is stationary. That is, it doesn't depend on whether we measure it today or tomorrow. The instance might be different, but the statistical properties, including the correlation function, would be the same. What that means in practice is that the correlation function does not depend on absolute time, doesn't depend where we start. It only depends on the difference between t and the t1, and so what we have here, in fact, is gkm. It still depends on those indices, but it depends actually on just t minus t1, rather than the t and the t1 independently. So why don't we use this notation and modify our integral to have that in? So it will be d by dt sigma of t is minus a sum over k and m, integral from 0 to t, gkm of t minus t1, q r double hat of t, q r double hat of t1. This should be qk and this should be qm. And then our sigma of t1 dt1. Okay, got a little bit simpler. At least we've got now the difference between the times rather than the absolute times. Now, time for yet another assumption, and that's the other one that is rather hard to justify, and I will have to give you a hand-waving argument to that. It's properly justified in the theory of generalized cumulant expansions. It's in our advanced course, so go take a look if you're interested. But for now, what I will say is the following. In typical liquids, the scale of time on which these correlation functions decay is in the picoseconds and nanoseconds. So the standard aqueous solution, for example, of a protein, or something non-viscous, acetone, things like that, it's in the picoseconds. The time scale of the evolution of our density matrix is the characteristic time scale of our coupling Hamiltonian, so in our case, maybe 100 kilohertz. And so we've got microsecond scale dynamics in here, but this thing decays on the time scale of nanoseconds, and picoseconds so much faster. So what we can say, and this is another perturbation theory type argument, is that the time evolution of the density matrix barely happens during the integration time. And so for the purposes of this integral, this is pretty much a constant. And so we remove the t as a 1 from the t, and we take it out of the integral. So dt1 becomes located there. So the so-called chorus gradient of time, simply stating that on the time scale of our integration, this density matrix is pretty much a constant. Right, so we've made a little bit further progress in here. We can now do a bit more about that integral. What I will now do is do a variable substitution. To get it a bit more convenient, what I will assume is I'll introduce a time tau, which will be t minus t1. So just making this a function of tau, and then t is tau plus t1, and t1 correspondingly is tau minus t minus tau. Is that right? Yep, it is. So let's replace all the instances of t1 with t and tau. So what we've got is then d by dt t, sigma of t is minus a sum over k and m, and integral, then g, k, m, that would be tau, then q double hat r of t, then q, this is k, and this is m, double hat r, t1 is t minus tau, dt1 is minus d tau, so d tau and a plus sign here, and then sigma of t. Right, the integration limits when t1 is equal to 0, tau is equal to t, and so if it's t tau, then we'll have a t here, and when the t1 is equal to t, tau is equal to 0, so we've got that. And finally, what I'll do is I'll switch the integration limits around and stick that minus in front, just as we previously had. So it will be a sum over km, integral from 0 to t, so with a minus in front now, gkm of tau, q, k, double hat r of t, q, m, r, double hat of t minus tau, d tau, sigma of t. There we are. The expression became neater still. And what we now need to do is to return back from the rotating frame into the lab frame representation, and we'll be done. So I'll remind you what those transformations were. They are given at the beginning of your handout. So we had defined our sigma of t as x plus I h naught t applied to rho of t. So we'll reintroduce this notation back and return to rho. And our h1r, double hat of t, was an x of plus I h naught t, h1 of t, x minus I h naught t. So let us take this. In this case, the operation will be applied to q's, and in this case just to sigma on this and on this side, and we will return back into the original lab frame representation, and you'll see a fairly compact final expression for the relaxation superoperator again. Okay, so we've got d by dt of sigma, so that is plus I h naught x plus I h naught t sigma of t. That is the first term in the product rule, then plus x plus I h naught t d by dt rho of t. So that's our right hand side, and the left hand side is going to be minus a sum over km integral from 0 to t, gkm of tau, then qk rotating frame of t is expanded in identically the same way as the Hamiltonian. The rotation operation is the same for every kind of operator that we've got. So it's e plus I h naught t, then qk double hat. Remember, the original operator was time independent. It was the rotating frame that gave it time dependence, so this is now static. So we've got e minus I h naught t here, then qm, but remember this t and tau, so we have e plus I h naught t, e plus I h naught tau, then qm double hat, and then e minus I h naught tau, and then e minus I h naught t. So double wrapping because we've got that, and also the sign is different. It is a minus here, And so what we've got is n minus here, but a plus in here. So tau has the signs that have been switched around, then d tau to close the integral, and finally e plus I h naught t sigma of t becomes the rho of t once we are out of the rotating frame. Right, quite a few things here would cancel, and let's see what it would be. So clearly this cancels. Then this cancels with this, they don't depend on the integration variable. This survives. Then in the result, what we have is this, this, and this are then again cancelled because this doesn't depend on the integration variables, and this is just here. And I think we're done. So we'll keep the derivative, and this should actually be rho. And so d by dt rho of t, so I've taken this derivative and I've kept it on the left hand side. I will take this term and I'll move it to the right hand side, so it will get a minus, it will be minus I h naught double hat rho of t, and minus the sum over k and m integral from 0 to t g k m of tau q k double hat. We've lost conjugate transpose on a few things, so I'll just make sure that we have it in here, double hat Hermitian conjugate, and it's wrapped before I actually get it in those exponentials. So e minus I h naught tau q m double hat Hermitian conjugate e plus I h naught tau, then d tau and rho of t ultimately here. And let me just put square brackets in this, like that. Let me double check with the handouts that I've done everything right here. Yeah, it's all completely fine. And so you see what we've got. We have, if we forget about this bracket, our usual Liouville-von Neumann equation with h naught. So it's as if the stochastic dynamics never happened. This is the situation where we would have completely ignored the noise. And the consequence of the noise is this enormous crocodile, which is a superoperator valued integral, about which we will make just one extra assumption. Remember, I told you that these functions decay really, really fast. Let's assume that they decay so fast that we can actually put the upper limit of this integral to infinity. And what this now is a superoperator valued Fourier transform. You see, these are just the usual Fourier terms. And h naught, superoperator, plays the role of frequency in here. And well, if we diagonalize it, it will just become a bunch of Fourier transforms. It's not usually convenient, so what people do, at least in the modern treatments at large scale, is to take this integral by brute force. And the whole thing is known as R double hat, or the relaxation superoperator, or the Redfield operator in the literature. So this huge, big integral. It can be computed because we know everything about it. We know what the Q's are because we know the rotational factorization of our interactions. It was done in the rotations lecture. Or if it's translationally modulated, we'll similarly get the translational factorization. We know the h naught. We can assume the correlation functions. That is the topic of the next lecture. And so this integral can be taken. And once it's taken, we just have this. So d by dt rho of t is minus I h naught rho of t. So that is the part that's completely deterministic. So all the hats in here, plus r double hat rho of t. And the presence of this extra term is the consequence of having that stochastic noise in the system. And we accomplished the goal that we set out to accomplish at the beginning of the lecture. We did express the resulting effect on the spin system in terms of statistical properties of the noise rather than the noise itself, and it is much more convenient in practice. So this is known in the trade as the master equation. It's not the end, however, because one extra thing that needs to be done to it before it can be practically used is the correction of the equilibrium state. These are, if you look at various practical electronic varieties, so let's say rotational modulated dipolar interaction, it's a negative definite matrix. And what it does is, it's simply under the action, it acts on the density matrix and it drives it to zero. The problem, however, is that it's driving it to zero rather than the thermal equilibrium. And so the next topic after we wipe the board is thermal equilibria and how to make these equations get the system into the equilibrium rather than the zero state. But before getting the system to equilibrium, let's first find out what that equilibrium is. By definition, a system at equilibrium, an ensemble of systems at equilibrium, would have the probability of each energy level given by the Boltzmann law. And so what we have is, say, a quantum system where we have diagonalized the time-independent part of the Hamiltonian, so h naught psi n, say, would be En, the nth level energy, psi n. And so we've got these energies, and the probability of having a system in energy level n would be, according to Boltzmann's law, an exp of minus En over kt divided by the partition function, so a sum over n exp minus En over kt. So if you remember the definition of the density matrix, we had probabilities there. We had them on the diagonal. So these p's, the probabilities of a system being in the energy level n, was the diagonal element of the density matrix, the nth element. And so from just that observation, and also from the fact that by definition in a thermally equilibrated system, the correlations between different molecules vanish, and so we don't have any off-diagonal elements either in there. So what we conclude is that our equilibrium density matrix is a sum over all energy levels, then x minus En over kt. That's this part of the probability, then psi n, the projector onto that level, and then we divide the whole thing by the partition function. So En x minus En over kt. But this is the definition of a matrix exponential. It's one of the recipes of computing the exponential of a Hamiltonian. Diagonalize, exponentiate every eigenvalue, do the backwards transformation. And so this, in fact, is the exponential of h. So it's x minus Hamiltonian operator divided by kt. Divided by, let's see what this is. This is basically the trace of that exponential, because we are summing every diagonal element, and it doesn't change under orthogonal transformations, so it's over the trace of the same exponential, minus h over kt. So that is the thermal equilibrium density matrix. Surprisingly simple, isn't it? We just take the Hamiltonian divided by the kt and exponentiate the thing, and that's the thermal equilibrium density matrix, not forgetting to divide it by its own trace. In Liouville space, it's a bit more complicated than that. We don't have the density matrix as a matrix, it's a vector, in which case this needs to be replaced with the right-hand side product superoperator, but that's a technicality. I won't stop on it. That's basically the expression for the Hilbert space, and it can be stretched into the Liouville space if you want to. Okay, so we know the expression for our equilibrium density matrix. It's fairly simple. So how do we make this equation, which we know for a fact drives the density matrix to 0, drive it to the correct thermal equilibrium? The reason why it doesn't do it automatically, by the way, is very subtle. It's to do with the fact that we had assumed classical character for our motion. Our spin dynamics is quantum mechanical, but our motion was, in a very subtle way, assumed to be classical in the treatment that we did. And that basically means that the lattice does not communicate the temperature to the system, and it basically relaxes to the infinite temperature. So we'll have to do a bit of tweaking now. It's very much ad hoc, but it works in practice. So one thing that we can do is to modify this equation to just drive it where necessary. And there are two ways of doing it, two primary ways, which are strictly speaking equivalent. We can do this, rho minus rho equilibrium, in which case this difference would be driven to 0. And that's nice, because if the difference is driven to 0, then rho of t is driven to the equilibrium density matrix, problem solved. However, what happens in practice is, you see, the previous equation was what mathematicians call uniform. That is, we just have rho, we have rho here, we could have taken it out as a bracket, and then the solution is a simple matrix exponential. In this case, we have a free term in there that doesn't depend on rho of t. So r times rho equilibrium, that's called a non-uniformity, and it complicates the calculations. So one way of getting around that is to rewrite this thing by doubling the matrix dimension. It's a fairly neat trick. So what we can say is d by dt of rho of t, but we will put rho equilibrium in here, so we just take our density matrix in the vectorized form, and we stick the equilibrium state vector just underneath it. You'll see why in a moment. So that would be, and we'll make a matrix here, block matrix, and this block will be IH double hat not plus R, so the usual Liouville von Neumann equation, minus R double hat, 0, 0, acting on the same vector, rho of t, rho equilibrium. So if we multiply out the first row of this matrix equation, we'll get d by dt rho t is minus IH not plus R rho t. So this part minus R rho equilibrium, that part. And when we multiply out the second line of it, d by dt rho equilibrium is 0, as it should be. But this equation is now uniform, so we can exponentiate these. This one big matrix, apply it to this vector, and just push the system forward as we usually do, and it will automatically relax to the thermal equilibrium. The practical performance of this, unfortunately, is not very satisfactory, because the matrix dimension doubles, and matrix operations have cubic scaling with the dimension, so typically the calculation length would go up by about a factor of 5 to a factor of 10 here. There's still a lot of zeros, and of course in sparse representations you don't need to store those zeros, but it still matters. And so a slightly neater way of doing the same type of transformation, it turns out to be possible to not double the matrix dimension, but just introduce one extra dimension into it. So let's do the following. Let's say we'll have d by dt of our rho 1, rho 2, and so on, rho n. So the elements of this state vector, they will be functions of time, of course. But let's stick an extra element in front and make it equal to 1. And then the following matrix, so 0, 0, 0 everywhere, because this 1 shouldn't change, and then minus R rho equilibrium, first element of that vector all the way to minus r row equilibrium. Second element of that vector, and then just the block of this. So this will be just minus I h naught plus r double hat applied to the same vector. So we'll have 1, then row 1 of t, row 2 of t, and so on, all the way to row n of t. This may be shown to be strictly equivalent to this, it's just we're a bit more careful with what we put where. So what we need to do in practice is to take our equilibrium state vector, multiply it by the relaxation superoperator, and put the result as the first column here. Put the usual I h naught plus r into this block, fill this with zeros, make sure we've got this 1 in front every time, and this equation is strictly equivalent to this. It will be driving the system to the correct thermal equilibrium. So this is the path where we phenomenologically correct this bracket, and so the system is driven to the correct thermal equilibrium. The alternative to it is to not modify this bracket, so to just leave a row of t as it was, but instead modify the relaxation superoperator. It is possible to rebalance the forward and backward transfer rates in there so that they drive the system to the correct thermal equilibrium. I will not give you the derivation for this. It is fairly complicated and we don't have the time really to properly justify it. But if we replace our r double hat with the following, r double hat exp minus h naught right product superoperator over kt. So right in this case doesn't refer to relaxation, it refers to a superoperator which multiplies something by the h naught from the right. So if we put this in place of r, then it will be driving the density matrix to the correct thermal equilibrium that's determined by the h naught naturally, without any doubling or other sorts of change to the matrix dimension. This is in practice a much more convenient way of doing it, because even though modern packages are relatively insensitive to matrix dimensions, you can just pass matrices of any dimension, and so long as they are consistent, they will be crunched. It's still sometimes problematic because there may be various independently evolving subspaces here which we would like to separate. And these jumping dimensions, they make things, the housekeeping operations involved in simulating these things a bit harder. And so we've got this as the default in our spinach library, for example. It just computes the R and multiplies it by this, and then equilibration happens automatically. We no longer need to worry about it. Right. The final topic for today is relaxation theory in the rotating frame. You probably noticed that when we returned into the lab frame, our h naught reappeared, and with it reappeared the Zeeman interaction, which is that gigahertz. And so it would be very inconvenient to propagate the system with the nanosecond timescale under that huge interaction. So it's oftentimes advantageous to not leave the rotating frame and carry the treatment directly in there. So what we have, what we derived was d by dt of R1. Density matrix was minus I h naught of rho of t plus r double hat rho of t. Let's take a closer look at h naught. It's a static interaction operator, stuff that doesn't depend on orientation, but it has the Zeeman part, which we would want to get rid of. It's very big but very simple, and it has the interaction part in it, so end. And we would ideally like to perform the rotating frame transformation with respect to the Zeeman interaction to get rid of the large terms, and then look very carefully at the evolution under h int, because typically the timescale here is at most a few hertz to a few kilohertz, depending on the Zeeman interactions that are offset with respect to the primary magnet frequency. So if we perform this rotating frame transformation, the fate of h int will be treated separately. There will be a separate lecture on the rotating frame, and the average Hamiltonian series that comes out of it, and R will also be moved into it and acquire a few terms. So we'll deal with them in a separate lecture that we'll be dealing with specifically that. What I will give you here is perhaps a qualitative picture of which terms survive in the Redfield superoperator and how they are called. Now, one thing that always remains invariant under the transformation with respect to the Zeeman interaction is the diagonal. So in principle, if we just keep the diagonal of the relaxation superoperator, that is very often good enough. So these diagonal terms are simply the terms that govern the decay of each state. So let's say we've got Lz here, L plus, L minus, and so on, all the other various operators that we've got in the Liouville space of our system. And this term in the relaxation matrix will just govern the decay of Lz, this the decay of L plus, and so on. And in fact, the standard T1 and T2 times are defined exactly that way. They are the corresponding diagonal terms of the Redfield superoperator. So if we compute such a scalar product, Lz, R, Lz, not forgetting to divide by the norm squared of Lz because it's not normalized, then this is R1 over 1 over T1. And T2 is defined as the element of the relaxation superoperator that governs the relaxation of transverse spin orders, single spin orders. So it will be, for example, L plus R double hat L plus divided by the square norm of L plus. So that's the T2. And there are various other things like TS, the singlet relaxation rate will be the same matrix element, but with respect to a singlet state and things like that. So simply just keeping the diagonal is oftentimes good enough. If we are not satisfied with that, if we specifically would like to see the transport of magnetization under the relaxation superoperator, for example, if we are looking at nuclear Overhauser effect, then the diagonal is not good enough, and we need to stick in a few off-diagonal terms. The next approximation in the quality of it is the approximation where we keep all terms and cross terms, importantly, of which all the cross terms are invariant with respect to the rotating frame transformation. So we'll keep all the cross terms that connect the longitudinal spin orders. So let's say Lz to Sz, or Lz to Lz, Sz, two spin order, things like that. So essentially we keep the diagonal and we keep the zero quantum terms. So no pluses, no minuses, just the z's. And if we move them all into the upper block and sort of wall this block off, so this is the zero quantum subspace where all the longitudinal operators live, and also all the operators that for various reasons are invariant under the Zeeman interaction. The picture resembles a kite and is for that reason known as the Redfield kite. And that's the minimum level of assumptions that's required to treat the longitudinal cross-relaxation processes such as nuclear Overhauser effect properly. The next level of accuracy is to also include cross-relaxation between those terms which have the same or approximately the same Zeeman frequency. Those are called the secular terms. The approximation is a bit dangerous because it's hard to decide often in practice which frequencies are equal. Some differences might be very small, others very large, and particularly for small differences this starts being iffy. So if your frequency differences you're confident about, then use it. If not, then probably the better idea is just to work in the lab frame where the problem doesn't arise to start with. So usually when we just do simulation of simple 1D, 2D, 3D experiments that don't involve Overhauser stages, we use just the diagonal. If we need to account for the nuclear Overhauser effect, we use the kite. It also includes cross correlations. And only in the most accurate experiments where fine details of intensities and such like are required and complicated cross-correlations are present, it is necessary to go to the secular form or even the Lau frame. Okay, that's the end of this lecture.